When we were working with functions of one independent variable, we found derivatives, which we denoted by y prime or f prime of x. Then we looked at the integral. Now the integral of f of x over an interval a to b gave us an area between the function and the x-axis. Now we'll look at functions with several variables. F of xy, so this would be a graph of a surface. And when we found the derivative of f of xy, because we had two independent variables, we fixed one of them and then found the derivative with respect to the other one. So we had partial derivatives of f with respect to x. That's where we fixed the y value as a constant and found the derivative, the rate that z was changing with respect to the change in x. Then we found the change in z, or the function f, with respect to y, and we did that by fixing the variable x and assuming that it was a constant. Now, if we had a third independent variable, we also had a partial derivative with respect to z. That was when we would find the change in w with respect to z, holding the x and the y both as constants. So now we're ready to start integrating multivariable functions. We'll have a double integral of the function over some region a in the xy plane. So the a is, the region is actually R, and that's the region in the xy plane. And we're going to be integrating then over an area of a region. So we'll look at that in just a moment. And if you were integrating a three independent variable function, you would be integrating over some solid region. D is some solid, which is a subset of R3. And we would have to use variables, the x, y, and the z, to describe that solid for the integration. Likewise, we'll use the double integral here, and we'll describe the x and the y values that describe that region R for our limits of integration. Okay, so now we have a solid that we're trying to find the volume of. That solid is bound between this function z equal f of xy, that's a surface in R3, and we're looking at the volume bound between that surface and the xy plane. So we're going to view that solid as a collection of boxes. It's in the second diagram. So we're going to take this region. Here's the region R in the xy plane. We're going to divide it into little pieces and little rectangles, and then we're going to take each of those rectangles and determine the volume of the box going up to the solid. Okay, so here's where we've divided the region R into rectangles, and we've divided this interval AB on the x-axis into subintervals, and each of the width of those subintervals will be our delta x. So delta x of k is just one of the random, subintervals there. And then we're dividing the interval CD, which is along the y-axis. We're dividing that interval into subregions, and each one of those will have width delta y sub k. So that's the width of one of these subintervals along the y-axis, and delta x is the width of one of the subintervals along the x-axis. So now we choose a random point in each one of these rectangles. So if we choose a point here, that box that would have that base in the xy plane would have a volume of delta x sub k, delta y sub k, times whatever the height is of that function. So f of x sub k, y sub k. So that's just a random point in that box, and we get the height. So that's just giving us the z value up in that, on that solid, on that surface, and that will be the height. So we've got our length times our width times our height to give us the volume of that one little rectangular prism. So this is a partition of R. where we've divided the x-axis and the y-axis into subintervals. Okay, so we take the one random partition entry in the partition of R. So we've got that one little rectangle. We'll look at a point in that interval, in that little rectangular region, and find the height corresponding to that z value on the surface for that point. And then we're going to assume that every point in that little rectangle has that same height. So this is very similar to the Riemann sums. So we'll use that for the height for that one rectangular prism, and then we calculate the volume. So we'll find that one volume, and then we'll do that for each one of the subintervals, the little partitions, the little rectangular regions, and then we increase the number of those little pieces, so the number of rectangles that are used in the partition of R. So as we increase the number of those rectangular regions, you'll see that we're getting closer and closer to what the actual volume is of the solid, bound above by that surface and below by the XY plane. So we're taking the height times the length along the x-axis times the length along the y-axis, which is, this is the area of that little rectangular region. And then we're going to sum all those up for all the different rectangular regions. And then we're going to take the limit as n goes to infinity. Now n here is referring to the number. So k goes from 1 to n. N is the number of those rectangular regions in that partition of R. So taking that limit is what's going to give us that volume. And the way we're going to denote that is using an integral. So this limit, now sometimes instead of saying that n goes to infinity, you might say that delta goes to 0, and that's referring to the diagonal of the biggest one of those rectangular regions. So essentially what that's saying is that you're letting those rectangular regions get smaller and smaller. So add up all the volumes. This is the volume of one of those little rectangular prisms. Sum them all up. Let the size of them goes to 0, which means you're getting more and more of them. And then the way we're going to represent that is by a double integral over the region R. R is the region that we partitioned down in the XY plane. And then we just got the function as the integrand, and then we have dA for that, which is representing that delta area of that one region. Now the dA, we're going to break into a delta x, delta y, so that we can then integrate with respect to x and then with respect to y. So the double integral is defined to be this limit, if it exists, and then R is just the region that we're looking at in the XY plane. F is said to be integrable if that limit does exist. So the function is integrable. This is a double integral. That's what we use notation-wise to represent that infinite, that limit of that sum. And then if f is non-negative, now that function f could have gone above or below the x-axis, but if f is non-negative, then what we're actually finding with this double integral is the volume of that solid. So that's what it would represent if the function f does lie above the XY plane.